All right, now we're going to do something quite different. So that last problem was very, very heavy on the analytic representation of functions, meaning as formulas. That's one of the four. We're trying to look at a variety of things. These are now getting back to the word problems. So these are the optimization problems that we've talked about a few times earlier this semester. This is going to be very, very real-world applications, things that you maybe can use in your real life. So it's almost required that the first optimization problem you do in a calculus class is some variation on this one. So a farmer has a certain length of fence, let's say 1,200 meters. She wants to build a rectangular pen, a rectangular enclosure for, you choose whatever animals you want to put in there. Llamas, chickens, whatever your favorite kind of animal is, you can make it for this. And the question is, what dimensions will result in the largest area for her animals? She wants to be as kind to her animals as she can. In this case, you might be able to guess the answer in advance. But just because you can guess what the answer is doesn't mean you've proved it. Calculus will let us look at actually all of the infinitely many possible configurations of fence that she could use and let us pick the best one. And even if you can guess this one, my bet is that most of the other ones that we're going to do this week, you won't be able to guess the answer in advance. We really do need calculus to do that. So I like to start off these by making it clear what our goal is, because especially as we get into some of the more complicated ones, there can be a lot of different things flying around in the problem, and you can get confused later on about what your goal was. And in this case, our goal is always going to be to maximize or minimize something, right? We're going to use our techniques that we found earlier for finding extrema in these very applied problems. In this case, our goal is to maximize the area. So I hope that what you'll recognize as we go through these problems that they're all going to follow a certain pattern. Identify the goal. Now let's write a function for the thing, or let's draw a picture first. So suppose that this is what the pen looks like. And she calls this the length and this the width. So then we have a formula for the area. We could call the area A. And the area of a rectangle is length times width. So this is the function whose maximum we want to find. We know how to find the maximum of a function using calculus. What's the problem, though? How is this function different than all the functions whose maxes and mins we found earlier this semester? The problem is that here we have a function of two variables. And this is a single variable calculus class. So we don't know how to maximize a function of more than one variable. You can go on and take Math E21A, multivariable calculus, and study that topic. So we need to get this function down to just one variable. So we need A as a function of one variable. And this is going to be the pattern in virtually all of these problems. So that means there must be some other information in the problem that we know that we haven't used yet. So at this point, you should go back and look at what other information there is. In this case, the information is the 1,200 meters. So we also know that 1,200 is going to be the total amount of fence that's used. So we should be able to write a formula that involves W and L in 1,200. And in fact, what is it? It's W plus L plus another W plus another L. So it's 2W plus 2L. So by using this, which sometimes is called the constraint, right? This is constraining you from building a pen that's as big as you want. You only have 1,200 meters of fence. This constraint will let us solve for one of these variables. We'll solve for one, and then stick it back into here, and then we'll have A as a function of just one variable. In almost every case, it'll be easier to solve for one variable than the other here, and you should spend 15 seconds deciding that now to save yourself 5 minutes of trouble later. In this case, everything is perfectly symmetrical. It doesn't matter which variable we solve for. I'm going to solve for L. So I'm going to get 1,200 minus 2W equals 2L. So L is 600 minus W. Thus, I now have a formula for A entirely as a function of one variable. I have A of W. A was length times width. Length is 600 minus W times W. Length times width. I just substituted this expression for L into my formula for A. So now we've succeeded. We've got our formula down, our function as A as a function of just one variable, which is exactly what we want. Now we can employ all of our powerful machinery from calculus to find the maximum of this function. As written, if we were going to take the derivative, we'd have to use the product rule. That would be fine, but we can save ourselves the trouble of that by multiplying out here. 600w minus w squared. So now we can take a prime, just using our normal derivative rules. We get 600 minus 2w. We should ask ourselves, can this ever be undefined? It can't, because this is just a linear function. So all that remains is to set this equal to 0, 600 minus 2w. And if we solve, we'll get w equals 300, which might be what you guessed. Now, we're still not sure, though, right? This might be, what are we supposed to do now? After we find the critical point, we're supposed to do one more thing before we just say this is the answer. We're supposed to check to see if this is the max, right? So is this the max? For all that we know, this could be the min. This could be the way to give the animals the least amount of room. We want to make sure this is the maximum. And so for that, we do our normal number line. Some books call this number line the first derivative test, by the way. I don't think we've used that language yet, but if you see it, that's what it's referring to. So I'm not going to write out all of the things that we're plugging in here because this is not so hard. If I pick a number less than 300, like 0, and I plug it in here, I get a positive, which means a is increasing. Is that what we were hoping for? Sure is. Pick a number out here like 400. 600 minus 2 times 400 is a negative. So yes, this is the max. Exactly what we wanted. Incidentally, for every one of these, not everyone, for most of these optimization problems that we're about to do, we have an applet. And it's not clear to me whether you would be better to explore that applet at the start of the video or at the end of the video or both. So if you feel like as soon as the problem is written and you read it, pausing the video and then going ahead and playing around with the applet, please do that. Have we fully answered the question? Not quite, because the question asks what are the dimensions. So we know that w is 300. And if w is 300, how do we find out what L is? Well, look, we've got an equation for L right there. 600 minus 300 equals 300. So the optimal dimensions are what you might have guessed, 300 by 300, in other words, forming a square. 300 feet by 300. And if you look at the graph in the applet, you'll see that the graph of the area function looks like this. This is the area function. And this maximum value right up there is at 300. So this says if you build something that's very narrow, you don't get much total area. If you build something that's very wide, you don't get very much total area. But if you build something that's halfway in between, a square, that's when you get the most possible area. So again, you might have been able to guess that. For the other future ones, I think you probably won't guess that. If you haven't already checked out the applet for this one, please check it out, and then we'll do some more optimization problems.